Hi, welcome to es346 Basic Thermodynamics. This is examples, and this is a polytropic compression work. I'm Lord Peterson. So here's the problem we're going to solve today. We have a piston cylinder device, and it's compressed while some heat transfer is occurring. The pressure and temperature is measured during this compression, and we wanted to determine how much work was required to do the compression. We're also told the initial volume is 2 cubic meters. So over here on the right, here's our cylinder, and we're exerting a force downward on here in order to accomplish this compression. We're measuring the temperature as that occurs. If this is a well-fitting piston cylinder, the mass inside will remain constant, the pressure would go up, and the problem also says that there is some heat transfer occurring. So the temperature is not constant, but it is also not completely insulated. Therefore, this is a polytropic process. And so what we want to do is determine the amount of work. But what we're not given is that polytropic exponent. So what we're going to do in this problem is determine what that polytropic exponent is, because it's required in order to use our boundary work equation. So remember that a polytropic process is described by this equation, where we have the pressure is some constant times V to the minus N, or C is some arbitrary, or not arbitrary constant, but some constant, and N is our polytropic exponent, and this is the total volume. Well, what we can do is we can use our pressure and our temperature in order to determine what our volume is, because we know that P times V is equal to mRT, right? Well, we can also do this in terms of specific volume, and we know that PV is equal to RT. So how does this little v and this big V get related? Well, we can go ahead and substitute in for big V with little v, and this will become a constant times the mass times little v, and all of that to the minus n. And I can go ahead and pull out that, or factor out that minus n. So I have a constant mass to the little n, v to the little n. And now all of this right here, since the mass is constant, n is a constant, c is a constant, that's all some new constant. I'll just call that equal to c prime times little v to the minus n. And then we'll see why that's going to become a little bit more convenient. So how am I going to, given a values of p and t, get n? Well, what I'm going to do is I'm going to go ahead and solve for v using this equation here. And then I'm going to go ahead and use this equation here to find out what n is. I'm going to get that by, if I take the log of both sides of this equation, so I have p is equal to c prime v to the minus n, I would have natural log of p is equal to the natural log of c prime minus n times the natural log of v. And notice that this has the form of y is equal to mx plus b, where this is my intercept b. These are my two variables, x and y. And now minus n is my slope. So I'm going to plot natural log of p with the natural log of v in order to determine from the slope what my value n is. So let's do that. And I'm going to go ahead and go into Excel to do that. So here I've moved into Excel. And what I have is the pressure and the temperature. And the temperature was given in degrees Celsius. And so since we're using the ideal gas law, we're going to have to do that in terms of Kelvin. So I'm going to make this column temperature in terms of Kelvin, and that will be equal to this right here, plus 273. So we can go ahead and copy that down for everything. So there's my temperature in absolute. And now we'll make this column equal to V. Remember, V is equal to R times T over P. So let's go ahead and do that. And R for air is 0.287. Multiply that by the temperature, absolute, divided by the pressure, and there's what my specific volumes are. So we'll go ahead and copy that down. And remember, I need to go ahead and plot the natural log of P and the natural log of V. So let's make this column here the natural log of V, so being equal to the natural log of this column right here. And we're going to need to do on the y-axis the natural log of P. So I'll do that equal to the natural log of this column right over here. All right, and now let's go ahead and just copy and paste these down. Give us all of our values that we have, and so there we go. Now we can go ahead and plot this chart. So let's go ahead and insert a chart in here. We'll do a scatter plot, and there's our data, and what we realize is it looks pretty linear, and so what we want to do now is do a curve fit. So let's have Excel add a trend line for us, and as you see it looks very, very linear. It's good, and let's look at what the equation is, and there we go. We'll make that just a, so I'm going to make that a little bigger for you. Not really easy. Okay, so if you look though, you can see that the intercept is minus 1.22. So that's what the slope is. So let's go ahead and go back to our problem here. And what we just saw was that n is equal to 1.22. It was minus 1.22, but minus n in here, in terms of that, this equation right over here would be positive m. So the slope was minus 1.22, therefore n is a positive 1.22. All right, so let's go ahead and continue on with our problem. So we saw that n is equal to 1.22 in this problem. And we saw in the video that the equation for boundary work for a polytropic process is P2 V2 minus P1 V1 all over, that would be minus n plus 1. So we need our big volumes. We had little volume on the previous slide, so let's go ahead and calculate what that is. V1, which we know the initial volume, that was equal to the mass times little v, and that right there was equal to 2 cubic meters that was given. So we can calculate what the mass is, and the mass therefore is going to be equal to big V over little v, or 2 cubic meters over 0.855. That was from our Excel spreadsheet. So that tells us that our initial volume was 2.34 cubic meters. And now I can use this mass, because that's fixed, to calculate what the final volume is. The final volume again will be m times v2. So that mass of 2.34, oh, I'm sorry, that's not meters cubed, that's 2.34 kilograms. 2.34 kilograms, and the final specific volume was 0.357. It's again on that Excel spreadsheet. So I see that the final total volume is 0.835 cubic meters. So now let's go ahead and plug that into my equation over here for boundary work. So the final pressure was 300 kilopascals. The final total volume was 0.835. And then I'm going to subtract P1, which is 100, and V1, which is 2. And then divide that all by minus 1.22 plus 1. And then if I do that arithmetic, I realize it's about 210 kilojoules. In fact, it's a minus 210, and you might wonder what this minus sign means. And the minus sign, as we'll see further, just indicates the direction. And what that means is that the force, the person that was doing the work out here lost 210 kilojoules when they did the compression, and then 210 kilojoules was gained by the system right in here. So there was a positive 210 going in and a minus 210 leaving the system. It's all indicating what the direction is. So the number that really matters is 210 kilojoules of work was done. Actually, I just went back and recalculated this and realized that's not 210. I'm getting about 230 kilojoules. So I must have made a error there on the first time I typed it in my calculator. All the steps are the same, just the numeric value is a little different.